Okay, folks, so what I want to talk about is the metric system and certain things about the metric system, as well as then conversions, how we're going to do conversions here, and I'm going to show two different ways of doing conversions. Right, so the reason why we're doing this via video is because you've done this like how many times during your academic career, and so this should just really be review. So the metric system is a very specific system of measurement, and the reason why we like the metric system is because this is, most importantly, a base 10 system, i.e. it is a decimal system. And that's what makes it nice, because we're not dealing with all sorts of weird conversion factors. Everything is factors of 10, right? For example, there are, 8 fluid ounces in a cup, but 2 cups in a pint, 2 pints in a quart, 4 quarts in a gallon, right? Like, what's that about? There are 12 inches in a foot, 3 feet in a yard, 6 yards in a furlong, I think, or something along those lines. Like, none of that makes sense. 5 bushels in a peck. Those are volume measurements that exist in the imperial system. There's no sort of consistent standard in the imperial system for what the conversion has to be, right? What is it? 1,760 yards in a mile. Like, what's that about? It's because all of those individual units of measurements were created totally independent of each other, and then someone had to link them together, and they just found what worked to link them together. But that's what happens when you're trying to cobble together a system piecemeal, right? Because the imperial system, which is all those other measurements, wasn't made at the same time. It was made over the course of hundreds of years, and then they just connected new measurements every time they came up with something. They're like, oh, you use that system of measurement, cool, we'll take that in, and here's the conversion factor. Whereas the metric system was created holistically and all at the same time between 1779 and 1799 in Paris. So they were able to put together a system and make it coherent, so there's a logical way of doing all the conversions, right? And so our metric system is based off a couple of what are called base units. So what are our base units? Well, for time, the base unit is going to be the second. For mass, the base unit is going to be the gram, and for distance, the base unit is going to be the meter. And everything that we do from there, then we put a prefix in front of the seconds, the grams, or the meter in order to give it meaning based on the powers of 10. So what we're going to do here is we're going to talk about what all the powers of 10 that we care about in terms of the prefixes, and give you what their meaning is, and then we'll kind of go from there. So we're going to use the meter as our example. So I'm going to put that in the middle of my page here. So 1 meter, right? And so if I want to write 1 meter, I would just write 1 little m. If I'm going to write that in scientific notation, that's actually 10 to the 0 meters, okay? So here we go. Let's talk about what all the different prefixes are, and that's what this column here is going to be. So some common ones. We're going to have centi, so 1 centimeter. Actually, I won't even use this column because I'll just write it here, 1 centimeter. And so we know that that's 1 cm. Another common one, 1 millimeter. 1 little m, little m. Another common one is 1 kilometer, or kilo is the prefix, so 1 km. And those are the most common ones. Now you may know things like deci, that would actually go in here, or deca or hecta would go in here, but we don't use those in physics, so we're not going to talk about them. We're just going to use the ones that we generally talk about. So let's go up the scale here. The next one up here is what's called megameter. So the prefix here is mega. Actually, I'll just underline the prefixes because that is good practice then, right? And so the symbol for megameter, we're out of m's here. I already did that. I get it. So it's going to be 1 capital M, little m. And then I'm going to have 1 gigameter up here. and giga being our SI, our metric system prefix. I say SI because it's called the Système International, because it is French and my French accent is terrible, so please don't tell your French teacher that I just did that. So that's one. Since it's a large unit of measurement, we're going to use capital G, little m. There you go. Now, there are things above gigameter as well. There's something called a terameter, right? Tera, like you may know it from a terabyte when you're talking about your hard drives and whatnot. And then there's things even larger than that. But once again, in the scale of what we're studying, we're just going to go up to giga, and that's it. Now, going back down, smaller than a millimeter is going to be the micrometer. And so I'll underline micro, and I'm totally out of M's now. And so what happens when you're totally out of M's is we tend to actually start using Greek letters. And so we're going to use the Greek lowercase letter m, which is mu, right? That is a mu. I'm just going to put that up here, mu, and it looks like a funny U, but it's not a U, it's a mu. There it is. That's the lowercase Greek letter m, mu. And then there's one below this that I want as well, which is the nanometer. Okay, and I can underline that, and that is 1 nm. Okay, and there are things lower than nanometer. We have the attometer and the femtometer and whatnot, the picometer. But once again, in the scale of our course, we're going between giga and nano. We're not going outside of those. So these are the ones that I need you to memorize, right? You need to know them. So here we go. How big are these? Well, I've written it in scientific notation here. I've written it here. I'm going to write it also just out as well, right? So actually, let me move this all the way out here, 10 to the 0 meters, right? As I said, it's 1 meter. So a centimeter we know is 0.01 meters. A millimeter, 0.001 meters, right? Centi meaning 100th, so 100th of a meter. Milli, 1,000th of a meter. Micro is a millionth of a meter. So 1, 2, 3, 4, there we go, 6. And then nano is a billionth of a meter. Okay, now those are kind of, they look weird, but if I put this in scientific notation, patterns start to emerge. This is 10 to the negative 2 meters. This is 10 to the negative 3 meters. Micro as millionth is 10 to the negative 6 meters. Here, 10 to the negative 9th meters. So if you notice, outside of here, where like deci is 10 to the negative 1 meter, we have a prefix every 3 numbers here. Kind of the same going up. A kilometer we know is 1,000 meters. Megameter is 1,000,000 meters, right? And giga is 1,000,000,000 meters. And so we seem to have another prefix every time we kind of go up 3 levels here. And rather than calling them levels, I'm going to give another name for it. When we're talking about the power of 10 associated with a given measurement, we have a name for that. It is called the order of magnitude. Probably should have more space there. The order of magnitude. So in other words, giga is of the order of magnitude of 9. Megameter is order of magnitude of 6. Kilometer, order of magnitude of 3. Meters, order of magnitude of 0. Centi, order of magnitude of -2. Milli, -3. Micro, -6. Nano, -9. So for example, if I write the number 4,7,382 meters, right? I say, what's the order of magnitude of this thing? We would say, oh, okay, well, if I were to put that into scientific notation, it'd be 4.7382 times 10 to the 4 meters. This would be of order of magnitude 4, okay? So it's relative scale. So there we go. Now we need to know how to convert between them. So let's look at an example, and I'm going to show 2 methodologies. If I have something that is 0.04743 centimeters, and I want to know how many kilometers that is, okay? Now, one way we can do this is by using what's called the factor label method that you probably learned in chemistry last year. And so that is using proportions in order to do this. So if I have that many centimeters, you could do this in one step. I would tend to do this in two. The first thing I would do is I want to multiply by this to get rid of centimeters. So I'm going to put centimeters down here, and I know a conversion between meters and centimeters. I know in 1 meter there are 100 centimeters. So there you go. And the next thing I want to do is now the centimeters would cancel out and I'd be left in meters. So I want to get rid of meters and put in kilometers. And I go, okay, well, I know the conversion there. There are 1,000 meters in 1 kilometer. And so there we go. Centimeters would go away, meters would go away, and I would get my answer in kilometers. So it would be 100 times 1,000. So that's 0.0743, and that's kilometers. And so I'm not done there because I need to put that in regular scientific notation. So if I do that, then that would be well, actually, let's look at this. That top would be 7.43 times 10 to the negative 2. And then on the bottom here, I have 10 to the 5th. Right, 1, 2, 3, 4, 5, and so kilometers. When I put that into finalized version there, 7.43 times 10 to the negative 7th kilometers, because we know that when we have exponent rules, that would have to flip up into the numerator and it would pick up a negative sign. So there you go. So there's my answer. Boom. And so there's kind of 2 steps here in the factor label method. One is doing your portions out in order to get that, and then to finish up the scientific notation work. I find that people have a lot of problems with the factor label method, even though it's perfectly acceptable, right? I'm going to show you another method. Because I think the thing with factor labels, people mess up what goes on top, what goes on bottom in each of these, and people sometimes mess up what these ratios are. Like, do I put the 100 up there or put it down there? I always forget, I'm not sure, boom. So let me give you another process. So the first thing that we're going to do in this process, and this process, by the way, only works for the metric system because it's a decimal system. So here we go. The first thing what we're going to do is we're going to write the order of magnitude of each. Okay? So for example, we're doing the same example here. I'm going from, let's pretend I don't know the answer, centi to kilo. So the order of magnitude of centi is -2. The order of magnitude of kilo is 3. So now I've got the order of magnitude. Awesome. The second thing what I'm going to do then is I am going to subtract the new order of magnitude from the old, right? In other words, I'm going to do here -2 minus 3, okay? Because the order of magnitude, the new one, here's 3. Subtract the new from the old. I know that probably that sentence structure is a little bit confusing. So here is the old minus the new, if you would just want to look at it this way. Old minus new. And that gives me -5. So what I'm going to do here is then I take the answer from that as an exponent of 10. Or, so in other words, what I'm going to say here is that means 10 to the -5th, right? So whatever this number is becomes that. So now my answer is 0.0743 times 10 to the -5th kilometers. So now all I need to do is I need to put this in regular scientific notation. Okay, and so the easiest way to do that is just convert your original number here. So 7.43 times 10 to the -2 times 10 to the -5 kilometers, and I'm left with 7.43 times 10 to the -7th kilometers. Got the same result in both ways. I like this method better when we're talking about the metric system because we can really exploit our orders of magnitude. It's a much more systemic process. I don't have to remember what goes where I just have to know the orders of magnitude and memorize the orders of magnitude of all of those. But you'd have to do that anyway in order to know the conversion factors. So there you go. So whichever of these two methods is the one that makes you happy to be alive is what you should do. But you have to be able to do them consistently and correctly. And so you're going to do some practice based on that we're then going to look at in another class once you've done with that practice. So there you go.